All right, so that's just a repeat of what I was saying earlier. Does that make sense, though? This is not the only case that you see it. There are other cases where you expect it to be sp3, but because of the pi conjugated bonding network, it turns out it's sp2. The lone pair just goes in there. In fact, there's one in the homework, end of chapter problems, which I didn't assign. All right, so I'm going to leave this now, acids and bases, and we're going to talk about Lewis acids and bases. A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. Let's look at a pretty strong Lewis acid. This is a strong Lewis acid. When we do Lewis acid-base reactions, we always draw the Lewis structure. So what makes BF3 a good Lewis acid? What makes BF3 a good Lewis acid is it wants another pair of electrons so that it can complete its octet. And so it can get another pair of electrons from the Lewis base. And so ammonia is a pretty good Lewis base. So we'll look at ammonia here. I'm not drawing these two correctly. For ammonia, what is the geometry of ammonia? Let me try to draw it a little bit better. We know that the electron geometry is tetrahedral. So I'm going to put the lone pair in this bond in the plane. That means this bond's going to stick out and this bond will stick in. And so it's got a tetrahedral electron geometry. Therefore, it must be what hybridization? sp3. So this lone pair sits in an sp3 orbital here. And its molecular geometry is trigonal pyramidal. Okay, so what's going to happen is this sp3 lone pair is just going to bond to this boron. There's an empty p orbital, correct? On boron. And so what we should form is an sp3p sigma bond. But, you know, they're repulsions. And those repulsions are going to try to minimize. And so what's going to happen is, in this case, it's not going to stay sp2. The boron's sp2, right? And so boron's sp2, and we should have a unhybridized p orbital. And so using VSEPR, we expect it to change hybridization. So let me draw this like this. You see, is this still recording? This is going to be a gap in the recording. Actually, I'm going to try to minimize. This is what we call staggered. You know, this fluorine fits between these two hydrogens, and this hydrogen between this fluorine is staggered. And so when that sp3p overlap occurs, that rehybridizes this, and now it's going to be sp3 hybridized. In fact, both of these will be sp3 hybridized. This will be sp3. Now, the interesting thing is both electrons for this bond came from nitrogen. And so both bonding electrons, came from nitrogen. And we have a name for that. This is called a coordinate covalent bond. Or dative bond. We have a name for that because normally one bond comes from, let's say, boron, one bond comes from nitrogen, and they share them. But in this case, both bonding electrons came from nitrogen. Well, this is going to come at a cost. And so what is the cost? The cost is the formal charge changed. And so nitrogen is no longer neutral like it was here. Now nitrogen is going to be short an electron because it gave one to boron. Boron's going to be ahead one electron. Normally this doesn't happen because nitrogen is more electronegative, but boron being short of an octet is unstable. And so in this case, it compensates. In other words, forming an octet gets priority over the unusual formal charge here. So the octet rule is the number one thing we look at. And so, yeah, the formal charges are strange. You know, they're reversed of what we'd expect. But that's the sacrifice that had to be made to get an octet. All right, so that's a Lewis acid-base reaction there. We'll take a look at another Lewis acid-base reaction here. And that's going to be the reaction between calcium oxide, solid, and water. So this is metal oxide. Metal oxide, that's an ionic compound, and so we're going to have calcium ions. Calcium has 2 valence electrons. If we lose both of them, we'll get calcium ion. And then oxide will gain those 2 electrons, will form the oxide ion. And this is going to be an ionic lattice, so it's just going to alternate calcium ions, oxide ions. And so we can generate the Lewis structure for the ionic compound. When we look at this, oxide is a good base. It's a good Bronsted base. It's also a good Lewis base. It's a good base. It's better if it's not locked in a lattice. It's kind of stuck in a lattice, so it's got to wait. You know, this is like a predator that's kind of stuck in the rock. It's got to wait for a fish to come by. The fish that comes by is water here. And so if water comes by, then we have something like this. Reaction occur. So what's a hybridization on oxide? What would you call it? It's sp3 hybridized. So there's an sp3 orbital here. And what kind of bond is this here? This is an S on hydrogen and an sp3 on oxygen. So this is an sp3 sigma bond, correct? Now the oxide's not going to go out and seek this. So let's say the water comes in and collides here. If the water comes in and collides here, then what happens is this sp3 orbital gets pushed into the s orbital. So this sp3 orbital with this pair of electrons gets pushed into this s orbital here. But is that okay to have 2 sp3 orbitals overlapping the same s? No, it's too many orbitals. And so what's got to happen is if this orbital gets pushed into this s orbital, then it's got to kick these electrons out into that sp3 orbital. And so the electrons get kicked out. And what do we form? So what we're going to form here is this. We're going to form a new bond. The new bond is going to be between this sp3 and that s. And we're going to break the old bond. The old bond is this s-sp3 sigma. So we're going to form a new s-sp3 sigma. The new s-sp3 sigma is going to be here, where we're going to take the sp3 that was on oxide and overlap it with the hydrogen's s. And then we break the old bond. The old bond, we lose those electrons and we end up with this. In other words, we end up with calcium hydroxide. Well, calcium hydroxide's soluble in water, and so this is aqueous. Calcium hydroxide aqueous just consists of calcium 2 plus aqueous ions plus 2 hydroxide aqueous ions. And so we'll have this occur here. And so what we say are metal oxides are basic. They tend to form hydroxide in water. Hydroxide is base. Let's look at a non-metal oxide. Our non-metal oxide is going to be CO2. And we'll react this with water. And so we're going to take CO2 gas and bubble it in liquid water. And so let's take a look at the Lewis acid-base reaction that occurs here. First off, we're going to look at CO2. CO2's Lewis structure looks like this. And then we analyze it. The oxygens here are electron pair donors, and they have a delta minus charge. And so these are what we call base sites, or base atom. This is delta minus. This has got a lone pair, so this is a base site. This carbon is delta plus. If it's delta plus, then it's capable of accepting a lone pair, but it's got too many bonds. If another bond comes in here, then we have to sacrifice one of these. Well, we can do that. We can just kick a pi bonding pair out onto the oxygen. And so we call this an acid site. And so CO2 technically is amphoteric. Amphoteric means it could go either way. It could be an acid or it could be a base. If we take a look at water, water is the same way. The hydrogen can accept a lone pair, so let's say an sp3 lone pair comes in and starts overlapping the s, it's going to kick these sp3 electrons out. And so these hydrogens, which are delta plus, are going to be acid sites. And the oxygen can donate, so that sp3 can push into wherever, an s or whatever. And so this will be the base site. So we have two potential reactions. One is this base on CO2 can attack the acid on H2O. The other potential reaction is the base on H2O can attack the acid site in CO2. And so we have two potential reactions. We'll look at those next time. So we're out of time. So